Welcome to the Bayes channel, which is all about Bayesian learning. And with this first video, I will explain what we mean by Bayesian learning from data. Now, the question that is at the core of machine learning and statistics is, how can humans and computers learn from data? Now, Bayesian methods are widely used in these fields, and in this channel, I plan to upload many short videos about many aspects of Bayesian learning. So, of course, a lot of theory, but also things like computation with MCMC algorithms, applications in other fields like philosophy of science, non-parametrics, hypothesis testing, bandits, reinforcement learning, and many more topics. But first, what is learning and what are the ingredients that we need for learning? We first have a learner, which can be a human or a computer. And the learner interacts with the world she wants to learn about via data, also called observations, examples, or just samples. And we can view data as finite initial segments ZT, which is Z1 up to ZT, of some infinite data stream, which we denote with Z omega. And the learner's task is inductive inference. Inference that progresses from given examples to hitherto unknown examples and to general observational statements. The learner needs to start with background assumptions that restrict the space of possible outcomes, and this is called prior knowledge or inductive bias. We shall see later that it's not possible to learn without prior knowledge or inductive bias. We assume that there is some collection of hypotheses that the learner can propose or investigate, and we can view an hypothesis as a general statement about the world. And in our context, machine learning and statistics, hypotheses are often expressed as a probability distribution over a sample space, and we call those statistical hypotheses. And a set of statistical hypotheses is called a statistical model or just a model. And a model captures the background assumptions mathematically. So it's a simplified description of the part of the world that we consider relevant. So let's do an example, coin tossing. Suppose we toss a coin with an unknown bias. If it lands heads, we denote a 0. If it lands tails, we denote a 1. Now the learner sees a finite string ZT of zeros and ones. We can model the tosses by a Bernoulli random variable with parameter theta in 0, 1. And a possible hypothesis is the coin is fair, and the corresponding statistical hypothesis is that the random variable z is Bernoulli distributed with the parameter theta is a half. Okay, let's turn to the learning objectives. The task of a learner is inductive inference, which can have 3 distinct objectives. Now, the first objective is estimation. For example, estimating a regression coefficient. Another objective is to predict or classify future data. For example, predicting how well a patient will respond to a certain medicine given patient characteristics such as white blood cell count, age, gender, etc. And a third objective is testing. So the learner is handed an hypothesis and some finite data sequence and is requested to conjecture an assessment, often binary valued, such as true or false or accept or reject. And there's also a dichotomy between exploratory and confirmatory research. So in exploratory research, the learner is given some data and asked to produce an hypothesis about the origin of the data. So you might, for example, be interested in understanding a possible genetic basis for a disease. So exploratory research is about finding the question, as Tukey said in 1980. And in confirmatory research, the validity of an existing hypothesis is tested. So in the coin tossing example, we can estimate the bias of the coin, or we can predict the next outcome, or we can test whether the coin is fair or not. Okay, so with the model in place and the data to our disposal, we need one more ingredient for induction, a method or a rule for inference. And in this channel, the focus is on Bayesian inference. Now, the essence of Bayesian inference is that it employs probability distributions both over statistical hypotheses as well as over data. So let's denote with theta a quantity of interest. Then the learner starts with specifying a prior distribution, pi theta, which quantifies her uncertainty about theta before seeing the data z. And then she calculates the posterior distribution, pi theta given z, the conditional density of theta given that the realization of z is a little z. And she calculates the posterior by Bayes' theorem, as shown here. So the numerator consists of the prior pi theta and the likelihood f z given theta. And the denominator is the marginal density of z, also called the Bayes marginal or the Bayes marginal likelihood or the model evidence. So the posterior distribution represents the learner's uncertainty regarding theta conditioned on the data. So it's a trade-off between the prior and the data distributions. which is determined by the strength of the prior information and the amount of data available. So that was the introduction about Bayesian learning from data. This was the very first video, and more is coming up soon.